This video is going to explain some of the results of the 2000 paper, The Program Size Complexity of Self-Assembled Squares, by Eric Winfrey and Paul Ruthmund. This paper was a response to Altman's open question at the time of what is the complexity of generating an n by n square in self-assembly. There are several related theorems that are presented in this paper. For a brief overview, Theorem 1 shows how you can construct a n by n square with n squared number of tile types. This is a trivial means of placing a unique tile for each position. Theorem 2 shows that you can make a improvement to this using only n plus 3 tile types, namely where n is a seed row, and use 2 tile types for a zigzag and 1 tile type for a filler. Theorem 3 goes over how we can use a log n construction by utilizing a binary counter to be the dominating source of complexity. Now, the paper also presents an interesting conclusion of the iterative exponentiation. This paper shows that we can construct a particular square that infinitely often that has a tile complexity of log star, discussed in a previous video. By infinitely often, meaning that we can prove that a particular square that we describe with this tile set will occur infinitely often. But not every intermediate square is necessarily a result of this, and is bound by the log star function of n. So, if we take a look at this tile set, it starts off looking like our regular log n construction with a binary counter in the lower left half. So what we see is a batch of zeros, and then there's some x filler tiles, and then there's an xy zigzag to the right of them, and then y filler tiles are filling up the bottom. Basically, we have a base square of, let's say, a size 10, and then we use this little 10 by 10 square as a seed row. For example, let's say we want to create a 10 by 24 square, let's say n is 10 to the 24, blah 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 blah.